Good morning again. The next lecture by Professor Banerjee, and I welcome again to all the participants and Professor Banerjee in this wonderful lecture series based on the advanced and the functional materials. And now Professor Banerjee is going to speak on exploring meta-stable phase in search of new function and prospective for the design of logic circuitry. So, Mr. Banerjee, you may please start.
Thank you, Tokeer. And thanks again for starting your week with us and staying for such a long time. Well, this is, I guess, one full week. So I'm going to talk a little bit about a really important emerging set of needs at the interface of energy and materials. And this has to do with computing materials for computing. And I'll explain why this is such an urgent need and discuss some possible solutions. So this is a collaboration between, that I'm privileged to lead across multiple departments at Texas A&M in science and in the Faculty of Science and in the College of Engineering across 6 departments that really bridges all the way from design of materials to entire systems. So let's take a step back and think about the history of computing. So in 1949, computers, there was a prediction by Popular Mechanics magazine that computers in the future may weigh less than 1.5 tons, right? So this is now true. Okay, we have, computers are a lot less than 1.5 tons, and this is something that, has been imperative to the progress of human society, being able to have portable, much smaller and much more effective computational tools, and moving perhaps those of you that have seen floppy disks at some point, which today's generation doesn't see. So we've seen in our lifetimes even this incredible progress in computing, what is called Moore's Law. So Gordon Moore was one of the founders of Intel, and he came up with this observation. So Moore's Law is not a physical law, but an observation that he made that the number of transistors and resistors on a chip doubles every 24 months. And there's lots of implications for this. So this means that the number of transistors and resistors not just doubles, but usually the price also goes down in half. And this has made computers a lot more affordable from what they were about 35 years ago, 40 years ago. So this is a schematic depiction of Moore's Law. So if you take a look at transistors, you've got this meteoric rise from the 1970s and 80s, about 6 orders of magnitude, a million-fold, and the typical sorts of computations that are possible, the number of junctions on a chip, the number of integrated circuits per square inch has all just dramatically increased over the last several decades. The challenge now, so is that a lot of this has happened by simply using engineering tools, by using, shouldn't say simply, by using some very sophisticated engineering tools, and by learning how to scale, particularly CMOS circuitry to ever smaller dimensions. So in the very first lecture of the series, Dr. D.D. Sarma talked a little bit about this, and he showed some examples of the smallest dimensions that are being reached. Now less than 12 nanometers are routinely being accessed. So what has happened over the last 3 decades is this enormous revolution in computing. So in the 1980s, this is again a set of periodic tables from Intel that I think are really instructive. In the 1980s, see, this is the part of the periodic table that was being used, mostly silicon and a few other elements. In the 1990s, you see a lot more. In the 2000s, now you're using elements pretty much across the entire set of periodic table, right? So what has happened in the last in the course of the last couple of decades is that semiconductor manufacturing, the computation has really become an advanced materials game, a functional materials game. And indeed, this is pretty relevant. Many PhDs that are graduating with degrees in chemistry, including many of my students, now work at Intel. So this is a huge game that has the development of advanced functional materials is critical to our computing future, and one could argue that our computing future is critical to the growth of technology as a whole, right? So as we start to run into the end of Moore's law, as these engineering tools run out of steam, we're going to need a whole new world of materials, a whole new world of physical mechanisms that can enable computing, right? So this is a comment from my colleague R. Stanley Williams. He's a professor of electrical engineering at Texas A&M, and he joined us after 25 years of a very successful career, rising to the top of Hewlett-Packard. And so one of the comments he's made recently is that the end of Moore's law could be the best thing that has happened in computing since the beginning of Moore's law. So the end of Moore's law, as we stand at this precipice, as we stand at this rather challenging time in the history of computing, where a lot of the advantages that have driven us are starting to run out of steam, there is incredible new opportunity to do entirely new things, to activate entirely new physical mechanisms, to think about how entirely new materials could be used to derive new function in computing. Okay, and so let's think about what the problem is. Why is Moore's law running out of steam? And why is it that we need new substitutes, right? And so this is not an engineering problem. This is a fundamental physical science problem, okay? So this is the structure of a field effect transistor. Again, this is something that you probably learn in some sort of physics class. You've got a source electrode and a drain electrode. So this is the typically heavily doped silicon here. In this case here, n-doped, and then you're connected to some sort of a current collector. And then you've got an active channel region, and then you've got a gate electrode and a gate dielectric right here in the middle. So these are 3-terminal transistors, right? And the current between the drain and source is controlled by the application of this gate voltage, right? So the gate voltage sort of acts like a valve, and it either shuts off or turns on this channel right here, and it does so by applying a voltage here. And if you've got depending on the sign of the voltage it applies, you can either introduce more charge carriers at this interface, or you can deplete charge carriers, and so you can either shut off the channel or you can turn it on, right? So now this has been a beautiful configuration that has worked really, really well for over 4 decades now. A 3-terminal transistor that is at the heart of all computing. This is an example of what sort of IV characteristics underpin this. So that's the drain current as a function of gate voltage, and this line here sort of shows you how that works. Now the challenge is that as we have kept shrinking the dimensions of transistors to ever smaller dimensions, these active dimensions have become really, really small. And so even when you are trying to keep this channel depleted, even when you're trying to have a transistor that is off, there is always some sort of leakage going on, okay? And this has some pretty profound implications for power dissipation. And so essentially, again, this is not an engineering problem, but because we've shrunk to such small dimensions, we essentially are on to off ratio has become much smaller, so our off current tends to be quite large. It's another issue that really is fundamentally related to the mechanism of turning this channel on or off is relates to the Fermi Dirac statistics of electron energies in a semiconductor. So essentially, if you apply a gate voltage, the steepness of this slope is 60 millivolts per decade. So if you basically get 1 decade increase in current for applying 60 millivolts, and you can't really get much more just based on the fundamental properties of a semiconductor. Okay, so essentially, as you get into smaller dimensions, the on to off ratios become smaller and smaller because you have to apply increasingly large voltages to get these large on to off ratios. And the more voltages you apply, the more there is leakage current, right? So the challenge that has arisen is a fundamental chemistry problem that arises and a fundamental physics problem that arises from the properties of semiconductors, right? And what it pertains to, every other property has scaled, but the one property that does not scale for a transistor with decreasing size is power, right? So essentially, the challenge is that you could use, you could run a chip at its full possible capacity, but you would generate so much heat just from having a very low on to off ratio and having a lot of leakage current that your chip would just run incredibly hot, would essentially melt a lot of components very quickly. Or alternatively, our other solution is to essentially not run the entire chip at the same time. And so that's calling it running it dark, right? So essentially, in your cell phones, you have more computing power than NASA had when they put a human on the moon, but we are starting to run into some really fundamental limitations. And you've sort of seen this. You perhaps have felt this yourself when you're trying to do a lot of things on your phone or on a laptop. You can feel it get really, really hot as you're trying to push the performance limits of the system, right? Okay, so essentially, again, this is the fundamental nature of a transistor, okay? And as you with existing CMOS technology, power dissipation is I off, which is the off current times the voltage cubed. And as these dimensions become smaller and smaller, you're not able to turn the channel completely off. So you always have some sort of current on here. And since this value is not zero, your power dissipation tends to be quite large, right? And so you're constantly sipping on power and consuming power. And you're limited in this by this 60 millivolts per decade. This is the best you can do in terms of the steepness of the subthreshold swings. So what we would really like is a transistor, an entirely different mode of transistor that instead of this purple curve here, will follow this red curve so that you can sit here and apply a very small voltage. And for applying a very small voltage, you'll get a very large increase in current, right? And so the off current is going to be very low, the on current is going to be very, very high. So you have to have a very large magnitude of change in current as a function of a very small voltage, right? So this is something that there's a lot of interest in devising these kinds of ideal switching behavior to replace this 60 millivolts per decade subthreshold swing that is intrinsic to most semiconductors, to silicon, right? Okay, so part of the challenge for this, so if you take a look at what Intel is doing, they've got two choices. They could run it gray, so they could basically run a large part of the real estate on a chip could run at diminished capacity, or they could run a few parts of the chip at full capacity and keep the rest of the chip dark. So that's the choice they've made. So the 22 nanometer node of our Intel at 3.6 gigahertz had a darkness ratio of 91.74%. So if you think about it, we've got this immense computational power, but we cannot fully harness it at any given point. 92% of the chip is kept dark. It's not powered at all. So it's just essentially turned off because we cannot afford to deal with the power. If we were able to supply all the power it needs, it would create so much heat. It would melt the chip. It would also so this is sort of fundamentally the challenge that we have. So how do we come up with much lower power paradigms for computing, right? And this is not just at the level of saying, okay, my computational power of my phone or my laptop is hitting some limits, and I'm going to have not be able to, expect more and more as time goes by. But there is a lot more to it, right? So we're on the cusp of this massive revolution in the internet brought a huge revolution to our lives. Now the next big revolution is the Internet of Things, right, where everything is networked, right? And this is slowly coming. It's on the way. The idea, one of the sort of biggest manifestations of that is autonomous driving systems, so autonomous cars, where we don't have to drive, but the cars become self-driving, and the cars automatically sense each other and respond to each other, respond to the road, and there's no human or minimal human intervention, right? So this is becoming more and more common. These network infrastructure, especially in times of natural disasters, to understand what is going on. So these are ideas that are increasingly prevalent. In the next 20 years. We're going to see a lot more of the Internet of Things. So we are becoming more and more reliant on computing, right? And at this point, about 5 to 15% of all energy consumption worldwide is simply used to process, store, and transmit information, as per the Department of Energy, right? So what does this mean? That we are talking about functional materials for energy. 15% of all energy, up to 15% of all energy, is simply being spent on moving electrons around, right? And so this is a huge drain on the grid, and this is a number that is continuing to increase. So we're going to have to do something about it before it becomes completely crippling, right? So data centers alone, centralized data centers, consume 205 terawatt hour of energy in 2018. So that's 1% of global energy consumption. Okay, so this is some very large numbers. So data centers are something that you might use to, for example, run a Google search, or maybe if you're using Google Drive, or in when we have a Cisco WebEx seminar, right? So you're using a data center, right? But so not everything you do is using a data center. If you're just writing a Word document, or if you're just doing something at home, preparing a PowerPoint presentation, you may not be using a data center. So even though you're only using the data center part of the time to use a computer, about 1% of global energy consumption is coming from here, right? And so part of this challenge also is that 90% of all data that is collected is discarded within 3 hours without any analysis whatsoever, because we don't have any way to analyze it, because we don't have enough computational power to analyze it, right? So we often have the ability to collect lots of data, but not the ability to store it or process it, and this is a huge challenge. So another again, if you look at some of these statistics are very startling. 50 zettabytes were generated, so that's 50 billion terabytes. If you think about having a 1 terabyte flash drive, that would be a pretty good flash drive or a hard drive. And then 50 billion times that, okay, were generated in 2020, and this number is going to increase by another millionfold by 2040, right? And so there's a lot of challenges in computing that have to do with all of this increasing consumption of information, our increasing reliance on computing, and then our sort of this world of autonomous systems, intelligence everywhere, and personalized medicine. Now, another thing that is also very important is that a lot of what we do now realizes on using computing infrastructure in the cloud. Okay, so if you do a Zoom meeting, for instance, you might have some minimal software on your computer, but a lot of what you're accessing is in the cloud. Okay, so a big part of what has to change is that computing can be done not just at the cloud, but also at the edge of the internet. So if you're driving a self-driving car, it just doesn't have time to send every piece of information it collects, okay, to the cloud, get a response back, and then respond, right? So it has to make split-second decisions, and so that means that a lot of the computing functions will have to be done, at the edge without having to go back to the cloud. So a lot of the computing decisions will have to be done by the sensor. So if there's a sensor that is picking up a certain signal, it has to make a decision very quickly without sending everything back to the cloud. So you need to have some sort of computational capability, some sort of intelligence that is built into the edge of the internet. So when we talk about all of this complex issues here, right, and how much energy is required in modern computing systems, well, there is an example, right? So what are these? I just, maybe you can enter your answers in the chat box. If you just take a look at this, what are you looking at? You're looking at pictures of dogs. Okay, so your brain came up with this answer, and you didn't need a lot of energy, maybe 20 watts of power, right? And you came up with this answer for 20 watts, maybe just a little bit of breakfast you had that powered this, okay? Whereas a current conventional computer would have required close to 1 million times this energy to make this decision, because it would have to, take a look at these pictures, it would have to segment it, it would have to compare it against databases of whatever it can find. Again, you would send the data, since you don't have, this is not the way search works, and we don't keep databases on our phones or our computers. You'd probably send it online to a data center where not someone, but a machine would essentially, an algorithm would take a look at the picture, segment it, compare it to all kinds of other pictures, and then give you back this decision. It might even make a bunch of mistakes, right? And it might even think that this person, this little guy here is a cat. So our human brain is a really exemplary computing system, right? And our human brain works with very low energy, with very low power input. It's not good at every type of computation. It is not the best type at computation if you're trying to multiply two numbers that are 14 digits by 14 digits. Okay, that's not what a human brain is great at, but it is excellent at what you just did, pattern recognition, right? And if you think about it, if you've got a little kid at home and you show them this picture, if they're maybe 2 years old, they might struggle to identify it. Maybe they'll think one of these is a cat, right? So again, as our brain becomes more mature, as you see more of the world, you become very good at pattern recognition. You also become very good at decision making, classification, optimization, and this is all done in a very energy efficient manner, right? So what if our computers work more like the human brain? Okay, then we could be doing a lot of computations much more quickly and with much less energy input, which would help us, a lot with this energy problem we're facing, and would also give us access to entirely new modes of computing. Really, it would enable this whole idea of artificial intelligence that we're so excited about. So what needs to happen is that we need to transform computing from what it's now, which is mostly arithmetic, right? Mostly arithmetic operations, into some sort of intelligence that looks like our nervous system, which is made out of neurons and synapses. And so one of the grand challenges that we've got is to create a new type of computer that can proactively interpret and learn from data, learn from its surroundings, solve problems that it has not seen before using what it has learned, and then operate with the efficiency of the human brain. So that's the dream. That's the big goal for sort of the next generation of computing, is how do we convert computers from things that do arithmetic to things that do intelligence. Every day you solve unfamiliar problems. You might be driving or through an area you've not driven before. You might be walking in an area that you've not walked before, and you use what you know to solve that problem. So if I drop you today in an entirely different city, you will figure it out because our brain is capable of adaptation, and it's capable of taking these lessons that you've learned and then being able to apply them in a new setting, right? And it does so without, in a very energy efficient manner. So this sounds like a great idea. This has been tried using conventional computers, conventional CMOS chips. So for instance, there's some big projects that have built out, 1 million neurons, multiple, billions of transistors, but essentially taking conventional chips and building neural networks comes nowhere close to achieving the energy efficiency or function of the human brain. So really the one conclusion that people, I think, can believe in is that we're going to need entirely new materials. We can't do this with conventional silicon, given all of its limitations. We're going to need entirely new materials. We're going to need entirely new systems that directly emulate the functionality of neurons and synapses. And then we have to be able to combine memory, computation, and communication into one fabric instead of this one Newman bottleneck of moving these around, right? So our challenge is to turn this tsunami of data that is coming our way and that continues to grow into human consumable information, right? So and just let's say between Professor Mao and I will give all these different lectures, and supposing you don't have 15 hours, how could you search through the lecture, right, for looking for something that you're looking for, right? Incredibly difficult. If we upload it on YouTube with modern algorithms, you're probably going to it's probably going to take you a few hours of combing through the videos to find something you need, right? So how do you convert this data tsunami into human consumable information, which involves emulating the computational capabilities of neurons, which include thresholding, integration, action potentials, by essentially using intrinsic material properties of instability. So using instabilities in materials, designing them across multiple length scales, and then dramatically increasing, data processing and throughput and energy efficiency at the level of architecture. So how do you move from, our goal is to move from this one Newman architecture to these neuromorphic architectures that are really fashioned like the human brain. And it doesn't mean that you have to entirely change your entire computer, but at least have accelerator chips that perform particularly different computing operations, okay? And then essentially utilize the physical measurement to perform a probabilistic calculations, especially when you need to do something like AI. Could you use these accelerator chips to perform these operations? And then adapt the architecture and come up with entirely new algorithms. So coding a computer that is built like the brain will be entirely different, but you will be able to code it to dynamically learn from its surroundings, right? So it's going to take this information and it's going to transform itself as time goes by, and essentially continuously grow, just like we do, just like when you complete your high school exam and your bachelor's and your master's, right? You're constantly increasing in your knowledge of chemistry. That's in your brain, and your brain is chemically transforming with the knowledge that you get, right? And this is the way our brain works. And somewhere you're storing this information that you might need at some point, perhaps during an exam. Okay, so that's how it's going to work. So you're going to need software that essentially learns in uncertain and changing environments. Okay, so the idea of linking neuroscience to computing is many years old, but only now are we starting to come up with materials, come up with designs and chips and such that can do something that is actually worthwhile. Okay, so one sort of computing that people have been very interested in, and it's just the beginning, is the idea of deep learning. Okay, it's a small set of AI, deep learning, where you try to model high-level abstractions and data using artificial neural networks. There's lots of options for neural networks, like I showed you, including silicon, but you just cannot fully realize the potential of neurons. And then the other challenge with deep learning is that you typically need these very large data sets, 1 to 100 million examples, 1 million to 100 million examples before you can do something meaningful. And if you get something that is outside the data set, it oftentimes will really struggle to figure out what's going on. It can be extremely inefficient in handling real-time updates. And so as you can sort of read through this list, you can see that this is not desirable for a lot of practical applications of AI. So when it encounters a new situation, it's going to have to entirely update itself, which is an extremely computationally expensive problem. Okay, and it's vulnerable to all sorts of issues. And then oftentimes AI can turn into a black box and give you an answer that is really not something that you fully understand. So there have been some pretty dramatic milestones, I would say, in just the last 5 years. In 2016, we had a computer program that beat a human at the Japanese game of Go. It's a complex strategy game that the Japanese experts spend decades learning, and they have so much experience in this. And for the first time, a computer was able to beat a human at that game. So that really brings to fore the power of deep learning. But we're still at a very primitive stage there. This is where we are today. There's a lot left to do as we handle these large streams of data. So the next sets of insight, or these next wave of intelligence demanding applications will require something that is very different from traditional processor-centric computing. Okay, and so there's 3 opportunities here. So for one, general purpose computing is hitting a wall. Okay, we are not going to be able to continue with business as usual for forever, not just because we're at the end of Moore's law, but also because we're fundamentally limited by the sorts of applications that can be performed by CMOS. Okay, then AI algorithms are quite poorly matched to general purpose hardware. So if you're going to want to use AI algorithms, you're going to need some entirely sort of intelligence type of hardware that functions a lot like our human brain does in terms of neurons and synapses. And really the idea here, and this is what I'm going to focus the rest of my talk on, because this is not a seminar on computing, this is not a series on computing. You can go to the computer science department and learn a whole lot more, but this is fundamentally about how materials connect to computing, right? So I'm going to then spend the rest of my time thinking about how new materials can enable entirely different types of computing, including in-memory computing and all kinds of deep brain architectures for solving very complex problems. And this is a so this is a chart from Hewlett Packard. This is a chart from Fujitsu. I just wanted to show you a couple of different perspectives, and then perhaps even beyond that lies a still more emerging area, quantum computing. But we're going to focus mostly here, something that will probably start being very dominant for the next 30 years, just like Moore's law has dominated, for the last 30 years, right? So okay, so let's again think about what is different about our brain, about the brains of animals in general. So in our brain, information is processed by neurons. And it's encoded in the magnitude and the timing of these pulses, right? So if you've got 4 different inputs, you're sitting in a room, and I don't know what sort of room you're sitting in. You're getting all kinds of different inputs. One input is me talking to you. One input is seeing my video. One input is seeing this computer screen. You might also be getting other inputs from someone sitting next to you. All of these inputs are coming in, and they're coming in with different magnitudes, and they're coming in with different spike timings, okay? And depending on how they land, if they are below a certain value, okay, you might ignore it. That's called thresholding, okay? Our human brain is, again, it's incredibly powerful, but we do not remember everything, right? If you ask me what I was doing, exactly 97 minutes ago, I don't know, because my brain decided to threshold that, right? So decided it's not important for me to remember what I was doing exactly then, right? But certain things that are important will get amplified and will result in an action potential that will fire and perhaps register somewhere. It's perhaps going to go in your brain and change some sort of set of weights in some sort of memory array, and perhaps you will remember this. Perhaps 10 years from now, if I make some impression on you, you will remember some part of this lecture because these pulses arrived and it got amplified, right? So there's a lot of incredible complexity, but you can break it down into a set of fundamental ideas like thresholding, amplifications, and then this leaky, integrate, and fire model. Okay, and so if we are going to build a computer that looks like the human brain, we're going to need a fundamental tool set of components for low energy, high performance memory centric computing, which includes oscillators, amplifiers, threshold switches, and then each of these components will actually replace thousands. One component that is built like a neuron can replace thousands and thousands of transistors, and you can essentially get multiple internal states with and replace lots of CMOS. But this requires identification of neuromorphic materials and then integration of the neuromorphic materials in the correct manner within structures to build this new tool set of materials. Here's some work by Stan Williams back in, there's a couple of papers in Nature in 2012 and 17 that demonstrates this with a compound called niobium oxide. So niobium oxide undergoes a insulated to metal transition at about above 900 degrees C, and using that insulated metal transition and the switching of the material from an insulator to a metal, okay, you can get all kinds of neuron-like functions. So you can see here this idea of a sub-threshold input that is filtered out, a super-threshold input that results in an amplification, an action potential, and then what you can start building from the structure. This is what the structure looks like. It's very simple. It's a two-terminal device, okay, where you've got titanium nitride, which is a metal, and platinum on two sides, and you've got niobium oxide in the middle. And you've got coupling of these metals. What you end up building are these oscillators. Okay, so you've got this sort of oscillator, and depending on the voltage applied and what's in the resistance and the capacitance in the network, you end up getting a chaotic oscillator. And a chaotic oscillator is really, really good for solving problems of global minimization, right? So a lot of times, if you don't have any noise, you might get stuck here. But with chaos, you can find the global solution to a problem. Okay, and this is sort of a very, this is an example. It's a two-terminal device with this niobium oxide. And what is unique about this niobium oxide is it exhibits something called memristance, and I'll tell you what that means in a second. But essentially, a memristor, a capacitor, and a resistor is being able to do the job of thousands of transistors in solving an optimization problem. So where something can land here and get stuck, if you've got this circuit here, it finds its way into the global minimum, right? And so again, it's a simple device. What is unique about the device? Okay, you can sort of see this here. And this is the beginning of the explanation of memristor. So at any given voltage, okay, you've got multiple, at least two, maybe even more, maybe even 5 different values of current, right? So let's say I pick this spot here. You get 1, 2, 3, 4, 5 different values of current, right? So you don't have a unique value of current. This is how this material is different from any other material, right? So if I take a regular semiconductor, if I take a regular metal, you know, from Ohm's law and such, that at a certain voltage, you're going to get a certain current depending on the resistance of the material, right? What memristance means is a little bit different. So the memristance means that the current at any given voltage will depend not just on its resistance, but on the memory of its resistance. So what is the resistance been set at based on what has happened in the past? And if you think about that way, if you think about it this way, that the resistance is not a fundamental immutable property, but something that can be set and reset into a different dimension. You can essentially then that resistance captures the history of the material. So what has happened to the material before, and depending on what has happened to the material before, you measure a certain current value. So this is how you sort of start to see how memory becomes part of computation, right? And this is exactly how your brain works in some senses, right? A certain memory has changed the resistance of a circuit in your brain. Okay, that circuit could have had multiple values. A certain thing has happened, a certain event has happened, and the memory, the resistance of that circuit has been set to a certain value by that event. And possibly over a period of time, that value can be reset because you have other important memories. We are constantly forgetting things, or if it was a very important, a life-changing event, then perhaps you're never going to touch the resistance of that memory. That's not going to change. Okay, so what this has implications for? So using this idea of chaos, using this idea of memristance and a resistance and a capacitor, okay, you can find really quick solutions to optimization problems. So if this is a landscape, right? Think about conventional computers as driving along with a truck and looking for the local minima. You'd have to drive all over before you identify that the local minimum, the global minimum lies here. Whereas using this oscillation-based computing with memristive materials is almost like flying over this space on a helicopter and being able to locate, okay, where the global minimum lies. So over here, for instance, if you fly over this mountain, you'll say, okay, well, there's a hole at the top. The global minimum is here. You can identify it. If you're just trying to drive around and you cannot see the top, you cannot see, you don't have the perspective, you'll struggle constantly. You know, it's going to take you a long time before you find the local minimum, the global minimum. The challenge is that it took Hewlett-Packard almost 5 years to find the set of conditions, the desired material, the desired set of circuit parameters, where you could get this chaotic dynamics that allowed them to mimic the neuron, right? So this was an immense effort. So how do we do this in a better way? So niobium oxide is not ideal because the transition temperature is above 900 degrees. It still consumes a lot of energy. So a challenge for us is to understand how these ideal neuronal functionalities like thresholding, amplification, integration, and then volatility, plasticity, right? So what is it that you remember in your short-term memory? What is it that you remember in your long-term memory, right? So you might remember what you had for breakfast today, but it's probably not important to remember it 10 years from now, so you will have forgotten, right? Whereas other things might be that you might actually go to class and want to learn something that will last with you for a long time, right? That's our hope, that some of these seminars, there will be not all volatility, there will be some plasticity as well, that you'll actually retain something, right? So what are the functions that will, what are the couplings of external fields to materials in terms of strain, current flow, temperature, that will give you the certain amplification, integration, plasticity behavior, and then to dial down even further, what sort of material properties do you need to get this set of circuit properties, and that will then allow you to replicate brain-like function. Okay, so again, I've tried to show you for all of the sorts of materials problems we've been tackling about what are the ideal, what is the wish list, what is the desired set of properties. And one set of properties we really need is a strongly nonlinear relationship between the voltage applied to the element and current flowing through it. So essentially, you'd like to have almost a spike, a step function, so that you can get a very sharp switch, a very low input power, so that you can get switching at attojoule spike energies at rates necessary for computational needs, an operating temperature that is within the range of desired operation. You want to be able to switch this more than 1 million times, and then having multiple internal states. So there's a lot of different properties that you need. You want to have these large electronic transitions with very minimal lattice distortions so that you can get the most energy efficient switching. Now, there's no real current set of materials that fulfills this entire set of conditions. So this is a open problem. We've got materials that perhaps will get 3 or 4 of these, but not all 5. So again, what we'd really like to get is a very sharp switch, okay, that we can switch and get a very large change in current. And we want to do this with very low input power to elicit switching at very these attojoule spike energies. And ideally, we're going to accomplish this, or we would want to accomplish this by having transitions that don't have a lot of atoms moving, because anytime there's a lot of atoms moving, you're going to struggle with heat generation. Okay, so so really what we need is materials that have highly nonlinear dynamical responses to external inputs, to voltage or current inputs. So you apply a certain voltage to it, and instead of simply giving you a relatively modest curve like silicon does or metal does, you'd like to see some action happening. You'd like to see a very large change in current as a function of the applied voltage. And there's lots of things to control here. Okay, this, how steep is this onset? How large is the contrast between the on state and the off state? Of course, we'd like this to be as large as possible. What is the hysteresis between the transition? If you go this way and or versus come back, this determines the volatility of the transition, right? Again, what is the sharpness with which this transition happens? And again, we would like to have not just materials that have this response, but then ideally something that encodes the history of the response. So again, let's think about this idea of membristance. So let's say I have a room, 2 rooms. We've got 3 switches in one room and 3 light bulbs in the other. How do you know if you only get to go to one room, each room once? How do you know which of these switches, 1, 2, 3, will map X, Y, Z light bulbs? This is mathematically impossible if you're only allowed to go to each room once, right? Here's what you could do, okay? You can turn, essentially you can turn 2 switches on, wait a little bit, okay, give it 5 minutes, turn one off and go into room B, right? So then the switch that remains on and the light that remains on, those 2 map. Then you can touch the 2 bulbs that are off, okay? And the one that's going to be warm was the switch that you had turned on and then turned off, right? And the one that will be cold was the switch that you never turned on, right? So essentially, even though at that given point, your singular observation is that only one bulb is on, by touching it, and you can learn about the history of what had happened. What switch did you turn on? What switch did you turn off? So that's the property we're looking for in the material, the idea of membristance, a resistance that is not just the property at this moment, but that also reflects what has happened to it in the past based on what sort of setting or resetting happened to it, right? Okay, so this is the idea. We're trying to derive a material that undergoes something like a change in conductance in response to external stimuli, and we want to be able to control these parameters, the conductance contrast, the hysteresis width, and so on and so forth. Okay, so we can frame neuromorphic computing then as a switching problem, right? How do you go back and forth between different materials and different states of a material? And I have introduced this concept of free energy landscapes in the past with respect to lithium-ion batteries and such. And so just like we talked about for any any composition, for instance, let's take the simplest possible idea of carbon. You can have one atomic configuration that's the most stable, that's graphite, and then another one that's diamond that is less stable, right? And what links graphite and diamond? That vector is pressure, okay? And same idea, you can have buckyballs and carbon nanotubes, but we don't want, getting from graphite to diamond is very difficult, right? You need to apply a lot of pressure. So what we'd instead like is this to have two polymorphs of a material, ideally with very different properties, maybe very different conductivities that are very close to each other and separated by a small barrier so that we can readily switch back and forth between these two. Now, it turns out it's pretty difficult to design these because anytime, primarily what is known as these COLA degrees of freedom, so spin, charge, orbital, lattice, and atomic degrees of freedom tend to be very strongly coupled. So if you change one thing, you change other properties as well. So it can be quite hard to navigate these systems to identify materials. So here's one way to think about this. So in the world of materials, okay, you've got a 23 orders of magnitude change in conductivity, right? So you've got something like silicon dioxide, which is what most of the Earth is made out of, that is completely insulating. And then you've got just in oxides alone, something like ruthenium dioxide that is completely metallic, right? And most compounds are neatly classified as being insulating or as being metallic or as being semiconductors. But there's a very small set of compounds that will transform between being insulating and being metallic, between being semiconducting and metallic. And here's an example: vanadium dioxide, which VO2, which undergoes a phase transition from an insulating phase to a metallic phase, and there's almost a 5 orders of magnitude change in its resistance. And this happens at a relatively low temperature. So it's essentially going from being like wood to being like steel, right? Massive change in conductivity, very abrupt, okay, suddenly triggered, in this case by temperature, but also by voltage. Okay, so generally speaking, the mechanisms for these can be structural, or it can be electronic, or a mix of both, typically a mix of different mechanisms. So you can have a system like VO2 or like a lot of charge density wave compounds where you've got this dimers along one crystallographic direction, and then as a function of increasing temperature or such, you end up having, instead of having this D1 and short D1 and long D3, you end up having a uniform bond length of D2, and this represents an insulating phase. This is a metallic phase. So this is a structural transformation. So atoms do move, and like if you recall what I had said, atoms moving will generally give rise to large entropies and a lot of heat generation. So Mott transitions are particularly interesting because you might be able to close the band gap here based on application of an electric field. So where you can essentially drive the transition with relatively small motion of the atoms. Okay, and this is a good way of thinking about this. So you've got the Mott criterion is the electron density times this Bohr radius. That has to be equal to 0.25. If this is met, the material becomes metallic, right? And so you can meet this criterion by different ways. You can either drive it by suddenly introducing a lot of electron density into this, for instance, by applying a electric field, or by increasing temperature, or you can facilitate. You can change this parameter. You can help get band overlap by strain, or by introducing somewhat of a phase transformation, or bringing the atoms closer to each other at a certain value. So these are some ideas. But again, if you take a look at this, we'd like to be in this regime, the more electronic regime, because this represents the most energy efficient way of doing a transition. Whereas the transition here with niobium oxide, this is almost entirely structural and is relatively energy guzzling. So if this is a compendium of, this is a compendium of all of the different possible materials that show metal insulator transitions. The temperature range we'd like to be in is between room temperature and about 400 Kelvin. That's about the temperature, max temperature of data centers where servers typically run very hot. Okay, we'd like to be in this range. So as nature is often cruel, most of the materials that show interesting behavior are at way too low of a temperature, right? Or at a much higher temperature. Here's niobium oxide that I was showing you. So there's relatively few compounds that are in this range, and this is a problem that my research group has worked on for the last 15 years. And the reason for this, again, like you see niobium oxide, 6 femtojoules per spike. This is quite energy intensive, and is not going to help us realize the full potential of neurons. Okay, so again, this is our wish list. We want to have this sharp switching, but we want to have it happen using mostly electronic transitions with relatively little lattice distortions, with very low input power. Okay, so I have about maybe 15 minutes left, and I will just to leave some time for questions. I'm going to talk about a few different mechanisms, from our recent work. All of this is very recent work. So this is work on VO2. Like I showed you, VO2 is one of the few examples of having a transition at a reasonable temperature, which happens to be 67 degrees. And the transition is mediated by this sort of structural transition, and this undimerization causes metallization, undimerization of vanadium chains. And so, that's shown here at low temperatures, or in the absence of applied voltage, you've got these dimers, and you also have this sort of canting along the c-axis, and then this material is IR transparent. And as you increase temperature, okay, the dimerization goes away. You've got one bond length here, and this becomes a metal, and it becomes the symmetry of the system increases at higher temperature. It becomes tetragonal, and you end up inducing this insulator to metal transition. There are some optical consequences to this that are also really, really interesting. And my talk 2 days from now will discuss this in the context of some critical energy, critical roadblocks to our energy transition. That's the theme of the last talk that I'll give, where I'll talk about, buildings in particular as something that have been really difficult to address. Okay, so one of the things that my group has done really early on is to come up with methods to grow from solution phase synthesis very high quality VO2 nanowires. And again, this is mostly the work of Louisa Whitaker Brooks here, and then carried on by Kate Pelcher and Diane Sellers and Eric Brand. And again, you can see here, this is in collaboration with Dr. Murthy Ganapathy's group. We can induce this voltage. We can drive this transition using voltage. And so the transition temperature, depending on what your application is either too high or it's too low. So one of our goals has been to modify it, perhaps push it up for computing applications or push it down to room temperature for other sorts of applications. And we can do this by introducing dopants, okay? And one set of dopants, for example, tungsten and molybdenum, can push the transition to room temperature or below. And this is an example of differential scanning calorimetry. This is an example of an actual device. Here's 1 nanowire of tungsten doped VO2. As you can see here, we brought the transition down, in very close to room temperature. So what is the role of tungsten? How is it that tungsten actually changes, the structure? So the tungsten that gets in here, tungsten is a larger atom. This is a high-angle angular dark field STEM image where you can image individual heavy atoms, and these individual heavy atoms, you can use this to map stresses. And these are some stress maps, and you can sort of see that these large dopants cause anisotropic stress in the system. And what ends up happening is that the tungsten doping induces severe local distortions that make that, because of the stresses that are induced, it makes the monoclinic phase less stable. So that goes up in energy. So the transition from monoclinic to rutile happens at a much lower temperature. So another way of thinking about it, by increasing the monoclinic, by increasing the energy of the monoclinic phase, you're moving the transition temperature from something like this to this, right? As it turns out, both enthalpic and entropic effects are involved. So what happens, again, based on X-ray spectroscopy studies, as well as these DEM studies, tungsten doping induces some severe local distortions that increase the thermodynamic force for the phase transition. Just locally around the tungsten atom, you have strain and a more symmetric lattice structure, and you can sort of see that here. The analogy is to a Trojan horse, right? So the tungsten atom introduces sort of a Trojan horse to this structure. So this is super interesting. This is a chemistry materials paper that Eric Bram spearheaded. Tungsten doping also really has an interesting effect on different effects on the heating and cooling transitions. So the heating transition is dominated by dopants, and so by introducing a dopant, you can change the transition relative phase stabilities, like we mentioned, and get the transition to happen at a lower or even higher temperature. But the cooling transition, okay, this has to do with the crystal symmetry, is determined not by the dopant, but by the defects present in the structure. And tungsten doping happens to reduce the defect density, and so it makes the transition very difficult because there's no oxygen or lower amount of oxygen vacancies. And so then this results in the transition being shifted down, and we end up getting a lot of hysteresis. So this is an example of what it's, this is a schematic illustration of what is going on during heating and cooling. So you end up, in undoped, you've got the heating transition is driven by defects, and the cooling transition by twinning faults, and the cooling transition is driven by oxygen vacancies. And this is true in both systems. There's enough twin faults in the monoclinic phase to nucleate the heating transition, but on its way down, since tungsten doping reduces the amount of oxygen vacancies, we end up having a severely depressed transition temperature. Okay, so this is a way to increase the hysteresis in the system. And this is some very recent work where we've actually decoupled hysteresis from the transition temperature through germanium doping. And the possibilities for introducing dopants are immense. Not just one dopant, you can introduce multiple dopants, you can have cations and anions. So really one big push here is to use a combination of machine learning and feature selection to get, can we start understanding the physical principles and encode this inside the system. Right? So that's been a big push for us. So again, the reality of this is that the transition from cold to hot, from the monoclinic phase to the rutile phase, is dominated by intrinsic thermodynamics, and it's really sort of dependent on the dopant modulation of relative phase stabilities. This is not nucleation limited because there's always these twin planes that are available to nucleate it. So the transition temperature is typically not nucleation limited. On the way back, when you don't have defects, okay, this turns out to be nucleation limited or defect mediated, particularly by oxygen vacancies. And this is I promised you I'd show you some examples of the consequences of this. You can see that here. And this is something we've been working on from the context of sustainable buildings. And this is the last lecture I'll be giving. And just to sort of say, also, we've got all these doped VO2 systems and undoped systems, and we can start building chaotic oscillators from there that can replace thousands of transistors and perform very complex computing applications using this edge of chaos behavior. So another very recent story just from last year, we were able to dope boron into VO2. We were able to do this through interstitial, we were able to accommodate boron in interstitial sites. We were able to do this through surface doping. And essentially what happens is that the boron has very different site preferences in the monoclinic and the rutile phase. So boron sits in one site in monoclinic and it sits in a different site in rutile. And so when you heat it up to the rutile, okay, it goes into its preferred structure there. But when you cool it down, it's stuck in an unfavored, disfavored site, and then it starts to relax. And so the transition temperature at any given time reflects not just its current status, but how long it's been since it was cooled down from the rutile phase. So it essentially starts to serve as a clock, and you can sort of see these different steps in here. Okay, so here's unrelaxed, relaxed, and intermediate relaxed, and the transition temperature is constantly increasing as the boron atoms relax from their metastable site into a stable site. So we can come up with a map of temperature and time, and it's a highly nonlinear dynamical map, but it provides an intrinsic mechanism for membristance in this system. Okay, so again, from an atomistic level, what's going on? So when you go into the rutile phase and you cool it down, the equivalent site for boron is a trigonal planar site, which is not stable. Okay, and so over a period of time, the boron atoms relax into a more favored tetrahedral site, and this journey is what causes a shift of the relaxation and a shift of the transition temperature. This provides direct experimental evidence of a metastable quench state and the evolution of the state as a function of temperature. Okay, and again, this can be used very directly to build transistors, showing a series of steps. So these are analog devices where the exact state of the system, again, depends on what has happened to it in the past. Again, this is work by Adelaide Bradisic with Dr. Patrick Schamberger. I'm going to play a little video that we made on this. So that tells you, that gives you an example of what it is that we're trying to do. I'm gonna move on here. So, okay, so by using different dopants, we can change the neuromorphic characteristics. We can change the transition temperature. And again, we're particularly, this has been a very important finding because this allows us to encode and history dependence into the structure of the material. So since my time is relatively limited, I'm going to tell you about one more example and then I'm going to stop. So this is some recent work we've done on an entirely different mechanism that has, again, a mostly electronic transition. And I've talked about different sorts of vanadium oxide phases in the past. So this is copper vanadium oxide, where we have a transition temperature that's actually extremely tunable across about 150 Kelvin, between 150 and 390 Kelvin as a function of the copper content. And we can trigger this transition not just using temperature, but also using current and voltage. And so what is the origin of this transition? So unlike most of these other systems, we can actually grow single crystals of this material, and we can solve the single crystal structure. And what we end up seeing is that the copper ions in this system actually oscillate, okay, between two very closely related sites inside this tunnel. And as they oscillate, their copper 1, they reduce the V2O5 to V4 plus, and the electron density that is associated with reduction of vanadium also then essentially starts oscillating. So this cation shuttling induces oscillation of the polaron that is formed inside the system. So at low temperature, copper occupies one of two very closely related sites, split sites inside a tunnel, and then at high temperature, it starts, it starts to diffuse between these two sites, and that results in a transformation of the material from being an insulator to being a metal. We can see this in hard X-ray photo emission spectroscopy. We can see this in resonant and elastic X-ray scattering. These are all evidences for this. And so what exactly happens? Copper states induce, based on DFT, copper states induce these states inside the band gap that actually end up shrinking the band gap quite a bit. And with more and more copper content, the band gap becomes very small. It's right at the cusp of the transition. And then when you apply temperature or voltage or some such stimulus, you end up closing the band gap and getting a metal insulator transition. So as you can see here, the more copper there is in the structure, smaller the band gap, lower the stimulus that is needed. And so higher the amount of copper, the less stimulus that is needed to induce the transition. Lower the amount of copper, the higher the temperature, higher the voltage threshold that is needed for this transition. Okay, so copper levels lie above the valence band, and these mid-gap copper states facilitate the polaronic transition. This is some X-ray emission results that show these copper 3D states, being transformed to delocalized states at the Fermi level. And if we are to do these ab initio molecular dynamics simulations, you can actually see this very small oscillation or shuttling of the copper ions. And as a result, the associated electron density on vanadium sites are shifted. And you go from being, having a insulating gap into having into closing the gap and having a metal. And so that small little transition here, this shuttling of the copper ions, just infinitesimally small, induces a really, really big change in electron density. So you kind of go from having localized copper to delocalized electron density from the polaron. And this is an example of an oscillator that we built, which is a critical feature of neuromorphic devices. So I'm going to skip, again, this is the fundamental mechanism, the shuttling of copper ions between the sites that then gives rise to, this mechanism of closing the band gap. So I'm going to skip this last section and really let me just finish by talking about, the big picture here is really what neuromorphic computing promises is to replicate the brain and a movement away from our conventional von Neumann architectures where we keep memory separate and processing separate. And you're constantly having to, do processing by going to the memory, looking at it, coming back, and doing a computation. But by integrating these all together, like our human brain functions, we have the opportunity to come up with a new paradigm of energy efficient and ultra fast computing. So metal insulator transition materials, so MOT materials that result from very subtle structural distortions or mid-gap states provide a very powerful means of accessing this. And fundamental mechanisms that collectively provide orders of magnitude improvement in speed and efficiency are really urgently required to build these artificial brains and to get us to these targets of attojoules per energy per spike and sub-picosecond to microsecond switching. So I want to thank the group. I've called out the folks that have done most of the work. So the work on boron dope BO2 with Diane Sellers and Eric Bram. The work on copper V2O5 was mostly Abhishek Parija and Justin Andrews and Joseph Handy. These two are together here. So thank you again for your attention, and I'm happy to take any questions you might have. Thank you.
Dr. Ufana Riaz.
Hello, Professor Banerjee. Hope you're doing good.
Thank you.
How many more years will the Moore's law hold true?
That's a good question. So Moore's law has actually lasted beyond when people predicted the end of it. So I think it's in some senses it's got a few years. In other senses, it's already ended because the power scaling, we live in this sort of post-Dennard regime where the power scaling has made it really impossible. So we're pretty much falling off the end of it. We're at the tail end of it, and we're going to need a solution in the next, certainly in the next decade, I would say, by any means.
Okay, so the next question is, what makes a language famous in artificial intelligence?
So I think probably the question has to do with sort of the software. Current artificial intelligence is still using conventional CMOS circuitry. And so people are trying to write the most efficient artificial neural networks that they can create, software implementations of using silicon circuitry. Once we move to entirely different hardware, of course, it's going to be interesting to see what sort of coding is required. It's going to be very different, and there's opportunities there for very energy efficient, very fast sorts of computing. Now, part of why we need to implement, part of the missing link here is the idea of developing compact models, right? So to do SPICE modeling, where you build out entire designs of chips, you need to have some very good parameters that describe the coupling of intrinsic material properties with extrinsic properties like the resistor and the capacitor. So those compact models are just currently being developed. There's a lot of progress, thanks to a lot of my colleagues in electrical engineering. There's a lot of progress, but those compact models need to be developed to then, inform the full design of the circuit layouts, and then that will hopefully allow the algorithm developers to just, come up with effective codes.
Okay, so the next question is how to perform data association using joint probabilistic data association.
So yeah, probabilistic computing is something that has gathered a lot of attention. And again, one proposal is to do probabilistic computing based on a physical measurement, right? And one example of that is a Bayesian inference engine that a lot of folks have been trying to build. And again, a neuromorphic architecture here would be extremely useful if we can build a Bayesian inference engine that will essentially react to or the inputs and perform a probabilistic physical measurement and give you an output rather than, an extremely computationally expensive architecture implementing that in a software implementation on current circuitry.
The next question is, please enlighten the concept of application of triangular norms in probabilistic metric spaces.
Triangular what?
Triangular norms.
Triangular norms?
Yeah.
So I'm not familiar with that term of triangular norms. In what sort of spaces?
Metric spaces.
In metric spaces. So yeah, I'm not sure. I think I need more clarification on that question. But it perhaps has to do with similar ideas of probabilistic computation, but I'm not sure.
Okay, so the next question is, aren't thermoresistors already discovered?
Oh yeah, I mean, thermoresistors have been known for a long time, since the 70s or even earlier. The idea here is you have intrinsic materials that are not just thermoresistors, but that encode a certain resistance that describes not just thermal history, but generally the voltage history, the current history of the system. Okay, so something that you can set and reset, and ideally have multiple internal states, right? The more internal states you have, the more sorts of more complex analog circuitry you can build out of it.
What are the other ions that we could use to dope vanidates to improve their band gap and their performance?
Yeah, so that's a great question. So I mean, we've done some work with silver vanadium oxides. There's entirely new mechanisms that we've also uncovered using p-block cations, and then we have some hydrated vanidates where it looks like proton diffusion is the fundamental mechanism. So there's some there's a lot of different mechanisms, and the reason this works is you've got a lattice that is pretty much has the ability to show a mix of ionicity and covalency, and that's at the cusp of being insulating and being metallic. The vanadium d orbitals are not too narrow, not too broad, so they're at the cusp of being able to, you can engineer it very finely depending on what else is in the system. And there's different mechanisms you can activate, such as lone pair induced distortions, or like I talked about, this shuttling of copper ions, or in the case of silver, there's a pinching of layers that then brings about a semiconductor to semiconductor transition.
So what is the role of these computational, aspects that we have explored in, improving the performance of devices or designing devices? I mean, how could it help in saving, in terms of saving energy, in terms of saving the chemicals that we use, to design devices? So if we could predict it before, yeah.
The goal is to use, again, one or two of these nonlinear dynamical devices. So like, for instance, a memristor with a resistor and a capacitor can replace thousands of CMOS transistors, and this is where the power of the whole sort of approach is. And together on the architectural level, you can get there are some simulations that have already been done that show about 1 million-fold improvements in energy efficiency that are possible using while also increasing the throughput of the computing operations. And so really this is going to enable a whole new paradigm of computing in terms of low energy computing, where you can really do a lot of applications much faster, and it's specifically for accelerator chips. So it's unlikely we're going to replace our entire computing infrastructure with brain-like computing. It's not necessary, but especially for the components that do AI, for accelerator chips, these are going to be a great option, and a very, very energy efficient option, because current AI chips are extremely energy consumptive.
How important is the metastable state in designing these devices? I mean, does it have any role the metastable state?
Yeah, so you have to have a metastable state, right? So you need to have at least two states that you can switch between, two internal states, and ideally we're looking for internal states that are very similar to each other in terms of lattice structure, that perhaps only have a difference in electronic structure. We're trying to minimize the how much of a lattice distortion there is. Ideally you'd have more than two, maybe even 5 or 6, and we've definitely seen examples of that where you've got multiple internal states that you can access in a system. But that's critical because you can't do this just with one state, right? So without being able to switch the material between two states, then you're left with a regular semiconductor like silicon, which then you're dependent on the Fermi Dirac electron energy distribution, which then confines you to 60 millivolts a decade for the sub-threshold strain.
Okay, so Professor Banerjee, I guess we are done with the question and answer round, and the discussions that were done were very, encouraging and motivating. I think the computational aspects which you have covered in logic circuitry was very informative in terms of designing devices, and the content was really captivating, a bit intense, but worth understanding since we have these advanced concepts, and it's high time for us to think of designing circuitries of all metal oxides, which we have known from the chemistry perspective. So I really thank you for sharing this unique lecture with us and showing us the other side of using these materials for designing and fabricating circuitries. And we are really grateful to you for sharing such wonderful information, and we are looking forward to your next lecture based on materials critically bottlenecks for energy, which is tomorrow, and I hope everyone's going to enjoy.
Day after tomorrow, right? That one.
Yeah, day after tomorrow.
That's great.
So thank you, Professor Banerjee, for being with us. Yeah.
Thank you, Dr. Riaz, and I very much appreciate you hosting me, and I'll look forward to seeing you day after tomorrow. Thank you.